Graham, the floor is yours. Thank you so much.
Thank you so much, Sachi, for the invitation and for the opportunity to speak and for organising this session. And greetings to everybody, and welcome and thank you all for coming. And I'm very conscious at the moment that while it's pretty easy really for me to come and talk for an hour or more about one of my favourite topics, it hasn't been an easy time in Sri Lanka, so it's probably a lot harder for some of you to come to this session and participate than it might be for me to do what I'm doing. So thank you very much for coming. It's good to see you all. So I'll screen share now with my slides. I'm talking about counting on networks. So when we think of networks, we might think of things like complex structures like this with nodes and links between them. And this is a network derived from academic citations in the graph layout field of academic papers citing each other. But networks of considerable complexity, of course, arise everywhere in today's world. We find them all over the place. They're really useful. So what I do in my work is I take a step back from the applications and work mostly on abstract models of these network structures. Now, why do I do that? I don't do that to retreat from the applications, from the practical side, from the real world. I do that because that's actually how you make your work more widely applicable. There's a popular conception that abstraction means removing from reality. That's actually not the case. By constructing good abstract models, you can work at a level that enables your algorithms, your methods, to be applied across a wide range of applications. And really with networks, we have a really wide range of applications. When we talk about abstract models of applications, we typically call networks graphs, but this is not graphs as in, axes and curves and so on. It's graphs with vertices, being abstract representations of the objects of the network, and edges representing the interactions between them. We can think of social networks with people linked by their friendships, communications networks, web pages being the nodes with hyperlinks between them as the edges, chemical networks representing molecular structures. I've mentioned academic papers and citations between them already. Having nodes represent countries and edges representing the borders between them is an old one. Graph theory representing all these different sort of areas, but originally it arose just in a recreational problem by Leonhard Euler in 1736. Now I'm just going to go through a few examples now of specific problems on networks and some of the counting problems I'm interested in, because that's my main research interest really on graphs, on networks, is counting things. Counting is really a fundamental human activity in any domain. So it's very natural to want to count structures of interest that we study in networks. Now, the first one I'm going to talk about is graph coloring. This arose in a recreational context, the study of map coloring, perhaps not quite recreational, but it became recreational. It was noticed in the mid-1800s that a map of England could be coloured in 4 colours, so that counties, each county gets a colour. Counties that share a common border get different colours so that they can be readily distinguished. And the question was asked, can every planar map, can every map on a flat surface be coloured in that way? And here's a map of Sri Lanka showing that the provinces of Sri Lanka can indeed be coloured by just 4 different colours, so that adjacent or provinces that share a common border get different colours. And you might wonder, can Sri Lanka be coloured with just 3 colours? So there's the first little exercise to think through. And if not, why not? Is there any evident structure in that map that makes you think, well, no, 3 colours is too few? Or if it can be done, how could it be done? But when we're looking at map colouring, we're not really interested in all the geographic details like the shape and terrain and so on. We're really just interested in whether borders exist between regions so that we can abstract it to a graph theory problem where what we are coloring is now the vertices, and the constraint is that adjacent vertices receive different colors. So here's a very simple graph: 4 vertices, 5 edges, and 3 different colors used, adjacent vertices getting different colors. Although map coloring doesn't seem an incredibly kind of serious or modern application of graph coloring, it's a really important area in practice these days. Graph coloring is important as a model of timetabling. For example, vertices can represent exams, colors can represent available time slots, and we put an edge between 2 vertices when 2 exams have a student in common, so that we don't want to schedule that student's exam or 2 of that student's exams in the same time slot. You know, if you ask me about whether that actually ever happens at Monash, I will give a strict no comment. But that's the ideal. That's the way we would like to do it. So we want, for the sake of efficiency, to use as few time slots as we can get away with. So we want to use as few colors as possible. The reason in this context why we might want to count colorings is to determine how many possible valid timetables there may be, or how many we may have to search through if we want to examine all possibilities to maybe see which suits our purpose best. And we have a function in graph theory called the chromatic polynomial that counts colorings. It takes as its arguments a graph and some proposed number of colors, Q, and its value is simply the number of colors, the number of proper colors satisfying this constraint that use that many colors or fewer. So it's colorings that are at least that good. And it's not obvious that it's a polynomial. It turns out to be, and that gives us the answer to many coloring problems, many counting problems, I should say, related to coloring on graphs. Graph coloring has other applications too, for example, in register allocation, in compiler design. If 2 variables in a program are used in the same part of a program, you don't want them to be allocated to the same register so that they are using the same register in the CPU at the time the computer is trying to compute with that part of the program. Given that constraint, you want to use as few registers as possible, or at least to ensure that you fit within the number of available registers. Another application is channel assignment, where you have cell phone towers, for example, and you want nearby towers to have different frequencies. So many different applications in scheduling, optimization, and communications. Okay, one fundamental property that the chromatic polynomial has, which ends up being central to this field of counting problems on graphs, is what we call the deletion-contraction relation. And it's really quite simple. If I want to color a graph so that vertices U and V receive different colors if they've got an edge between them, that's the constraint. Adjacent vertices receive different colors. If I want to color the graph with some number of colors Q so that the endpoints of some edge E use different colors, then how many ways that can be done? Well, I could just get rid of that edge so that there is no longer any direct constraint on the colors that U and V can have. So U and V in this graph could get the same colors, or they could get different colors. But that's too many, isn't it? Because we are allowing some colors, some colorings that we shouldn't have allowed because they give U and V the same color. So we want to subtract those, we want to remove them, and the colorings where U and V get the same colors are also colorings of the graph where U and V are identified. If U and V are to get the same colors, then as far as coloring is concerned, they may as well be the same vertex. So we have 2 graphs, each with 1 fewer edge than the original graph. And if we can evaluate the chromatic polynomial on each of these 2 graphs, and we take the difference between them, then that will give us the chromatic polynomial of the original graph G. So that's a recursive rule that we can use to compute compute the chromatic polynomial on any graph at all. And each time we apply the recursive rule, we get 2 new chromatic polynomials to compute, but they each have 1 fewer edge than what we started with. And I've got the notation G \E for G delete E. That's the graph we obtained by deleting the edge E between U and V. And the graph G /E, we call that contraction. We are contracting or shrinking the edge E so that its 2 endpoints come together and emerge. They become the same vertex. So that's a simple recursive rule for computing any chromatic polynomial. You know, if you're interested in algorithm analysis, if you've done some analysis of algorithms, have a think about what the time complexity of that might be, how long it might take to apply this recursive rule to compute the chromatic polynomial of a graph. Is this a good method algorithmically or not? Have a think about that for a moment. It's certainly a really important theoretical property of the chromatic polynomial. It's the foundation of most of its theory, but algorithmically, is it so good? Anyway, that's the deletion contraction rule for the chromatic polynomial. Encountering colorings, we have this constraint that adjacent vertices get different colors. Sometimes we are looking at more general colorings where we do allow adjacent vertices to get the same color, but we apply a different cost in such cases. And this is commonly done in statistical physics using mathematical objects called partition functions, where we allow any coloring at all, but the colorings are weighted according to how many good edges with identical endpoint, good edges with differently colored endpoints and bad edges with identically colored endpoints. So in this particular coloring with the green and the blue there, the good edges are the black ones. They have differently colored endpoints. The bad edges are the red ones. And in statistical physics, I won't sort of go into all the background to this, but a very important object is the partition function, which is a sum over all colorings, but it gives them different weights contributing to the sum according to the number of good or bad edges that they have. And this is really fundamental to anything you might want to do in doing statistical physics on large network models. Okay, another important counting problem on graphs is related to network reliability. So graphs are models of, among other things, communications networks. And we may imagine that the nodes now are people or communications devices, computers, whatever, and they have links between them. Each link is not infallible. It has a certain probability P of surviving and a corresponding probability 1 minus P of failing. And if we start with a connected network, we want the network to have a high probability that in the presence of random failures, the network still remains connected once some of the edges have failed, according to these probabilities. And in this very simple model, the edge failures are treated as independent and with identical probabilities. You can certainly imagine, and people do consider more complicated models, but this is the simplest case to get started. What we want for a network to be connected is for it to contain a spanning tree. That's a tree that includes every node of the network and is a minimal subnetwork with that property. So there's a unique path between any pair of vertices in a spanning tree. So it's the kind of minimal connected network you can have that links everything up. So you imagine in this all-terminal reliability scenario that each edge may be chosen or survive with probability P. And we want the chosen or surviving edges to contain a spanning tree. And we ask for the probability of that. The reliability is the probability that the set of chosen edges, randomly chosen in this way, contain a spanning tree. In other words, the probability that the network remains connected in the presence of all these random failures. Now, I gave this as an example of a counting problem on graphs, and here I've defined it actually as a probability. And this swapping back and forth between the counting viewpoint and the probability viewpoint happens all the time in this field, because after all, probability is just about counting the number of favorable possibilities and dividing it by the total number of all possibilities. So we hop back and forth between those two points of view pretty seamlessly. And one of the reasons that counting on networks is important is for the computation of probabilities of important properties or events on the network. Okay, so I've been throwing at you a variety of interesting problems on networks that have accounting or probability calculation as their main objective. And there are many others I could consider. In electrical engineering, for example, they are interested in flows on networks. Each edge carries a current. At each node, Kirchhoff's current law must be obeyed. The current in must equal the current out, and there are sort of other electrical principles as well. If the flows are taken from some fixed finite set of possibilities, then the number of flows in which there is no edge with zero current is something known as the flow polynomial, which is a very important polynomial in graph theory as well. Things we might like to count in graphs include major structures like spanning trees, forests or acyclic subgraphs, spanning subgraphs, which contain spanning trees. And that's, of course, related to the reliability polynomial we were just talking about. This, I've put here the weighted numerator of a linear code. Now, that's on the face of it, nothing to do with graph theory. It's something drawn from coding theory. And maybe I've already mentioned the Potts model from statistical physics. There's a closely related model called the Ising model. And I could get really carried away and start mentioning knot theory. That's right at the heart of pure mathematics. But the remarkable thing is that all these counting functions that I've mentioned so far belong to one very tight-knit, cohesive family. They can all be obtained from a single two-variable polynomial called the Tutt-Whitney polynomial. And we can think of this polynomial as a kind of, as computer scientists, we might call it a data structure that stores information about the answers to a wide variety of counting problems on graphs. So it not only, as we've seen, contains a lot of important, answers to counting important structures in graph theory, but it turns out to also contain answers to counting problems in statistical physics, knot theory, coding theory in communications. So it not only provides answers to interesting problems in graph theory, but it provides an interface to other disciplines. So I'll describe now what these Tutt-Whitney polynomials are. We will later look at some other counting problems that don't belong to this family. It certainly doesn't cover everything you might want to count if you're interested in counting on networks, but it's a really major family of structures that lies at the heart of the topic. Now, there's a really important function in graph theory called the rank function of a graph, and it assigns to each subset of the edge set this quantity. It's the number of vertices that those edges collectively meet minus the number of connected components of the subgraph that those edges collectively define. And the reason it's called rank is that it ties in very beautifully and precisely with the rank that you would have met if you've ever studied matrices or linear algebra. There are very tight connections between graph theory and linear algebra. Indeed, I would give a plug at this point. As computer scientists, one of the areas of mathematics that comes up most, I have found over many years, is linear algebra. So, piece of advice, never miss a chance to build up your skills in linear algebra. And here's another example where it comes in perhaps unexpectedly in the study of counting problems on graphs. So there's the rank function of a graph. There's an important polynomial called the Whitney rank generating function. It's a two-variable polynomial, so we'll call its variables x and y. we can obtain it by summing over all subsets of the edge set these binomial terms, x to a certain power, y to a certain power. And without getting too embroiled in the fine details here, the important things here is that the rank appears and the size of the set of edges, its cardinality, also appears. So the coefficients of this polynomial can be shown to count subsets of edges in a graph of a given size and a given rank. And given that size and rank of a set of edges are two of the most fundamental properties that a set of edges in a graph can have, counting these things by this polynomial is a really fundamental thing to be able to do. So that's the Whitney rank generating function. Another really important polynomial in this context is the Tut polynomial. This is another two-variable polynomial, and it can be defined in a number of ways. I'm giving you a recursive definition here. As with any recursive definition, there's a base case, in this case corresponding to a graph with no edges. I've got three recursive cases, one for the special case of an edge that is a bridge. So a bridge is just an edge that if you remove it, it breaks the graph up. It fragments the graph into more components. A loop is just a single edge that forms a circuit of length 1 at some vertex. So these are very special edges. They're sort of degenerate, I suppose you might say, in a sense. So they deserve to be treated as special cases. And every time we see a bridge, we introduce a factor X. Every time we see a loop, we introduce a factor Y. And you can see deletion and contraction coming in again. So I can delete the edge E in the graph, look at the Tut polynomial of the resulting graph. I can contract the edge E in the graph and look at its Tut polynomial, you know, recursive computation here. If the edge E is neither a bridge nor a loop, in other words, it's just a common or garden variety edge in the graph, I just form the Tut polynomials of the two graphs obtained by deletion and contraction and add them together. So that's my recursive rule for the Tut polynomial. Now, there's a certain amount of theory you've got to do to put this on a solid foundation. It's all very well for me to define it this way, but you have to prove mathematically that it is well defined, that the choice of edge doesn't make any difference to the end result of this recursive calculation. That all turns out to be the case. That can be done. I've got two quite separate polynomials here defined by quite separate methods due to Whitney and Tut, but they turn out to be intimately related. One of them is just a translation, a coordinate translation by one in each direction of the other. So you can move very readily between the two of them, and they both, in their own way, contain the same information but differently represented about counting problems on graphs. So these polynomials lie at the heart of enumerative graph theory. And the reason why these Tut-Whitney polynomials are so important to the field is the following theorem, which basically says that if you've got some function that depends only on the structure of the graph, not on the names that you call the vertices or the order you write them down in, and it satisfies some kind of deletion contraction relation, and whenever you have to compute it over separate components, you just multiply them, which is kind of what you would want to do. You know, when we've got different components in a graph, we think of them as independent. And if we're calculating probabilities of certain events on different components of a graph, we'd like to be able to multiply the probabilities and treat the components as independent. And in many situations, that's exactly what you want to do. So these conditions are really not very onerous. The heart of them really is the second one. But what this theorem is saying is that if you've got a deletion contraction relation, if you have a property of graphs or a number, an enumerative function on graphs, which can be recursively computed using deletion and contraction, then, provided it satisfies a couple of other really basic conditions, you can find it out from the Tut-Whitney polynomials. So, for example, We mentioned the chromatic polynomial before. It satisfied a deletion-contraction relation. There was a minus in there instead of a plus that we saw on the previous slide, but that doesn't really matter very much. As long as the recursion is linear, we find that it comes out of a Tut polynomial, or in this case, the Whitney rank generating function. So this is how to get chromatic polynomials from Tut-Whitney polynomials. Okay, so because I'll just get back a bit, because these Tut-Whitney polynomials have two variables, the way to explain what information they contain is best done by looking at the domain of the polynomial. So we have a function of two variables, so we can consider its domain to just be the XY plane, the real plane. And we can say, well, if I plug in particular values of X and Y to the polynomial, what information does it give me? And so that's what this diagram that I'm presenting now is intended to convey. I've mentioned the chromatic polynomial that counts colorings according to the number of colors that you're allowed. Well, appropriately evaluating Tut-Whitney polynomials at Y equals -1 will give you chromatic polynomials. I mentioned flow polynomials before. If I take Tut-Whitney polynomials and evaluate them along this vertical line, then it gives me the flow polynomial. I also mentioned the reliability polynomial to give us the probability of survival of a network that is subject to link failures. That polynomial can be obtained by evaluating Tut-Whitney polynomials along this line. I did mention, I did a bit of name dropping. I mentioned coding theory, that there's a very important object in coding theory in the study of communications called the weight enumerator of a linear code, and linear codes are a huge, practically important class of codes. And it turns out that weight enumerators can be obtained from Tut polynomials, not quite of graphs, but of slightly more general objects than graphs that are based on the linear structure of the code. I mentioned statistical physics, how there we have these Potts model partition functions. And if we evaluate these two variable Tut-Whitney polynomials along various hyperbolae, then they give us the Potts model partition functions. And yellow, perhaps it's not so easy to read, but I've mentioned the Jones polynomial here of an alternating link goes along these other yellow curves here, these other hyperbolae. So again, that's something from topology, something from pure maths that we get out of this. There are some points in the Tut polynomial plane here, the domain, that are very easy to evaluate. The two black hyperbolae are easy to evaluate, but they're actually a bit degenerate. They don't really contain much information. They're not so interesting. And there are some special points that are of particular interest as well as being easy to evaluate. In talking about some points in this domain being easy to evaluate, it then raises the question of, are they all easy to evaluate? And that, I guess, brings me back to the question I was asking earlier. When I first talked about chromatic polynomials, I raised the question of that binary linear recurrence we had for the chromatic polynomial. How useful would that be algorithmically? And you may have thought about that a bit, and you may have said to yourself quite correctly that, yes, each time I remove an edge, I double the number of polynomials I've got to evaluate. And so actually, although you can, in principle, evaluate the chromatic polynomial, and indeed all these polynomials that I've mentioned here, the entire Tut-Whitney two-variable polynomial, you can evaluate them all using these recurrences. Those algorithms take exponential time. So they are not fast algorithms, not mainly, although theoretically very important, but not useful practically if you want to actually get your hands on these polynomials. So as computer scientists, I know we'll want to talk more about the computational aspects of these things. So that's really what I want to spend a fair bit of time on now, the computational complexity of computing the answers to these and other counting problems on graphs. So basic definitions. If we have an algorithm A, then its time complexity is just a function of the input size n that gives us the maximum time that the algorithm takes over all possible inputs of that size. And we can say that the algorithm has polynomial time complexity if the time complexity is big O of n to some constant power. So exact time complexities are very difficult to work out. They're very complicated functions, but in classifying something as polynomial time complexity, we're really only wanting to give a very simple upper bound to the time complexity of the form some constant times input to some constant power. So the power is fixed, doesn't depend on the input, and this has to apply, that has to apply, in big O terms, or in other words, for sufficiently large inputs. So that's what polynomial time complexity means. And the best of all possible worlds is that we can solve our problems in polynomial time. So we're going to talk for a little bit now about decision problems. We are mainly talking today about counting problems, but in order to talk about the complexity of solving counting problems, in order to talk about the main ways of classifying the complexity of counting, I need to say a few words about decision problems and P and NP, which a few of you will have met. So a decider is an algorithm basically that just always gives the right answer to a decision problem. And a polynomial time decider is an algorithm that always gives the right answer and runs in polynomial time. So it's a polynomial time algorithm such that if the input X has a yes answer for the decision problem, the algorithm accepts it. And if the input X is a no answer for the decision problem, the algorithm rejects it. So by decision problem, I should say, I just mean a problem where we ask for inputs of a particular type, and typically in our scenarios, graphs, and we ask a question about the input, such as, is the given input graph connected? Does it have a triangle? Does it have a circuit? Is it bipartite? In other words, can we color each of the vertices black or white so that adjacent vertices get different colors? We want to divide the vertices into two camps, as it were, black and white, so that all the edges go across between the camps. We don't have an edge within the black camp. We don't have an edge within the white camp. So that's what is usually called a bipartite or two colorable graph. And we can ask for any input graph, is it of this type? Does a given graph have an Eulerian tour going right back to the origins of graph theory with Leonhard Euler, a sort of closed walk through the vertices and edges of the graph that uses each edge exactly once. You can repeat vertices, but you mustn't repeat edges. Each edge is used exactly once, no more, no less. Is a given graph planar? These are all questions with yes, no answers. So the computational problems here are decision problems, and a polynomial time decider is a polynomial time algorithm that always gives the right answer to that particular decision problem. And all the ones I've listed here have polynomial time deciders. And so we classify them in the complexity class P, being the set of decision problems that have a polynomial time decider. And if you studied algorithms in your computer science education, you will think through perhaps the methods that you might use to do this. If you want to tell if a graph is connected, a breadth-first search suitably conducted will do the job for you. Does a graph have a triangle? You can do local examination of the neighborhoods of each vertex, or if you want to be more rough and ready, you can just look at all triples of vertices and check them. That's a naive approach, but still polynomial time. And think about all these other cases. Some of them are a bit more complicated. Planarity is a bit more involved, but most of these, in fact, all except the last one, are well within undergraduate computer science curricula. So these are decision problems about graphs in P. All right, that's about deciding the answer from scratch. Then there's the famous complexity class NP, which is not about finding out the answer from scratch. It's about, loosely speaking, it's about verifying the answer once you've got it. Okay, would you know the answer if you fell over it? Okay, so we define this a little more formally with the notion of a polynomial time verifier. So if we have a decision problem, I mean, I should have put algorithm here. I wasn't really wanting to get into Turing machines, but ultimately all these notions get formulated if you want to formulate them really precisely, we do so with Turing machines. But for our purposes, a polynomial time verifier for some specific decision problem is a polynomial time algorithm that takes two things. It takes an input, which for us will mostly be a graph, or maybe a graph with a number, but we'll call it an X to try and be general. But alongside the input, there is extra information, which loosely we think of maybe as the answer, the thing we're looking for, the structure we're interested in. I'm going to be a bit more formal and call it a certificate, because actually it doesn't always have to be the exact answer. But anyway, the verifier takes the input and the certificate, and to satisfy the definition of a verifier, we require that if for our decision problem, the input is a yes input, that is, the answer should be yes, then there must exist some certificate Y such that the algorithm with that input and that certificate accepts. It may, for that same input, reject for other certificates, but as long as there's some certificate that leads to acceptance, that's okay. On the other hand, if the input is a no input, then every certificate must make the algorithm reject. There must be, in those cases, no acceptable certificate. So in other words, the input is a yes input if and only if it has a certificate which can be verified. So that's a quick definition of the class NP, stands for non-deterministic polynomial time. So here are some examples of decision problems in the class NP. You might remember some of these. Is a graph connected? Does it have a triangle? Does it have a circuit? Is it bipartite? Does it have an Eulerian tour? Is it planar? But we met them all before. They were in P, but they're in NP too. Certainly if our problem has a polynomial time decider, then that also serves as a polynomial time verifier, because we don't need a certificate. We just decide the answer in polynomial time. And if the answer is yes, well, then it always accepts. If the answer is no, well, it's always rejecting. So in these cases, in the decision problems that are in P, they are also in NP. And we can have a verifier just based on the polynomial time decider without using a certificate. It doesn't mean that we can't make our lives a bit easier with a certificate. For example, if my question, does a given graph have a circuit, I could propose that my certificate might actually be the circuit or a circuit in the graph. And once I've got a circuit, it's quite easy algorithmically to check that that circuit satisfies the definition of a circuit. You know, there's no repetition of nodes, and we go around, and you know, all the edges that are supposed to be there are there, and so on. So these all have polynomial time deciders that don't use certificates, but they'll have, sorry, these all have polynomial time deciders, and therefore these first half dozen at any rate, they also have polynomial time verifiers that don't use certificates, but that we can also often write other polynomial time verifiers for them that do use certificates and that do the verification a bit more easily than solving the problem from scratch. But further down, I've listed further problems that we haven't yet met in our discussion of P. And these are all decision problems that are not known to be in P. We don't know of any polynomial time decider for them. But we do have polynomial time verifiers. And to give the basic idea of the verifier, I've just written here what the certificate would be. For example, is a given graph three-colorable? In other words, can I color the vertices with at most 3 colors? Just like I was asking you about the map of Sri Lanka at the start, can I color the vertices with at most 3 colors so that adjacent vertices get different colors? Well, a certificate for that would be an actual 3 coloring, which can be very hard to find from scratch, but once you've got it, is efficiently verifiable. Does a given graph have a Hamiltonian circuit, a circuit that meets each vertex once and only once? The certificate would be the actual Hamiltonian circuit, easily verified once you've got it. So this is the idea of the class NP. So, and here is the landscape of P and NP visualized as a Venn diagram, the class P of decision problems with polynomial time deciders down the bottom, the much bigger class, or we believe it's much bigger, assuming P does not equal NP, but that's the biggest open problem in computer science, really. We don't know that, although we are in the habit of assuming it, but this is something we don't know. Fame and glory awaits any of you who can solve that problem. Conceptually, at the top of NP, there's a collection of hardest possible problems in NP that all other problems in NP can be computationally reduced to in polynomial time, and they are called the NP complete problems. And most of the problems that are listed lower down on the previous slide are NP complete decision problems. There was one exception there, the graph isomorphism problem. In other words, given 2 graphs, are they really the same, apart from maybe different names on the vertices? That's a problem that's known to be in NP, but it's not known to be decidable in polynomial time currently. Seems to be close, and not known yet to be NP complete, and believed not to be. So that's the world of decision problems, at least as far as P and NP are concerned. But now, with some of those concepts behind us, let's talk about counting problems. So in complexity theory, we have the class number P, although some people will call it sharp P, and a fortunately dwindling minority will call it hash P, but I'm going to call it number P because it's about counting the numbers of things. It's the class of counting problems that correspond to decision problems in NP. To put it a bit more formally, a problem is in number P, and this is not decision problems. It's a problem that asks for some number of things if it gives the number of valid certificates for each input for some polynomial time verifier. So to try and get across the essence of that idea, here are some of the decision problems we mentioned before. Does a graph have a triangle? Does it have a circuit? Does it have a 2 coloring, etc.? Are the 2 graphs isomorphic? 3 colorability, Hamiltonian circuit. Does a graph have a clique of a given size? A clique being a set of mutually adjacent vertices. For each of these problems, I can envisage a certificate, which, when the answer is yes, enables me to easily verify that answer. And the corresponding counting problem is just the problem of counting those certificates. So the corresponding counting problems in number P that come from these decision problems in NP are just the problems of counting triangles, counting circuits, counting 2 colorings, counting all area tours, counting isomorphisms, and so on. So that's what number P is. It's the class of counting problems that arise from decision problems in NP. And we can ask about their computational complexity. And it's not surprising that because we are asking for more in counting problems, we don't want to just know if the answer is yes or no. If the answer is yes, we want to know exactly how many. That's asking a lot. It's not surprising then that hard decision problems give rise to hard counting problems. And indeed, there's a collection of hardest members of the class number P, known as number P complete counting problems. And it's an empirical observation that whenever you have a decision problem that's NP complete, that's one of those hardest possible problems in NP, then its corresponding counting problem is number P complete. It's a hardest possible counting problem in number P. This is not something anybody has yet proved, but it's really just a lesson from experience. So hard decision problems lead to hard counting problems. What about easy decision problems? Well, easy decision problems can lead to easy counting problems. We wanted to know earlier if a graph has a triangle, and that's easy, and it's a little more work, but not much more work, to count the exact number of triangles in a graph. Similarly, it's not hard to count the number of two colorings of a graph once you've worked out the number of connected components that the graph has. Have a think about how you might do that. And some slightly more sophisticated algorithms, classical algorithms going back a long way, can be used to solve these other counting problems corresponding to easy decision problems. Counting spanning trees in a graph is a real classic, goes back to Kirchhoff over 150, 170 years ago, using determinants. Counting the number of perfect matchings in a planar graph. This is an interesting one, quite a tough one, using a relative of determinants called Pfaffians. A perfect matching is a set of edges which meets every vertex in the graph, but no vertex in the graph is incident with two of the edges in our set. So you can imagine a whole lot of disjoint edges. They're all disjoint from each other, but there have to be enough of them to cover the vertices. So that's what a perfect matching is. And it's polynomial time, not trivial, but polynomial time to work out if a graph has a perfect matching. If the graph is planar, we can even count them in polynomial time. Number of Euler tours in a directed graph can be counted in polynomial time. But perhaps a little less obviously, easy decision problems don't always lead to easy counting problems. There are many cases, and actually this turns out really to be more the rule than the exception. Easy decision problems can very often give rise to hard counting problems. So here are some counting problems where the corresponding decision problem is easy or even trivial, but the counting problems are all difficult. Counting cliques of all sizes in a graph, that's the total number of them. Counting cliques of at least some given size that you provide in the input, that's hard. It's hard to even determine if there is such a clique in general. But every graph has a clique, of small enough size. I mean, even a single vertex is a clique in its own right of size 0. So the existence problem here is trivial. If you count all cliques regardless of their sizes, even though the decision problem is trivial, the counting problem is hard. In particular, it's number P hard. It's at least as hard as anything in number P. Although counting perfect matchings can be done in polynomial time for planar graphs, it's number P hard for general graphs. Even if, in fact, it's even number P hard for bipartite graphs. Counting paths between two specific vertices in a graph is hard. Counting circuits wherever they may be in a graph is also hard. That was a little pet problem of mine in my PhD thesis days. Counting Euler tours in an undirected graph, that's hard, and so on. So here's a picture of the world of number P hardness. And if I were to put this picture next to my earlier picture of P and NP, then I would draw P and NP a lot smaller, because once we are getting up to the upper levels of number P, that's a really difficult complexity class. So these problems are, tough. So getting back to the sort of family of counting problems captured by the Tutt-Whitney polynomials that I was talking about earlier in the talk, having hopefully sold you the idea that these Tutt-Whitney polynomials are really important. They capture lots of important information about a wide variety of counting problems. Well, then we want to know how easy they are to compute. And unfortunately, if we want to compute the entire polynomial for all graphs, no matter what the input graph is, that's number P hard, has been known for a long time. If we restrict to bipartite graphs, it's still number P hard. Even if we restrict to planar bipartite graphs, planar graphs of maximum degree 3, still number P hard. There is some good news. If we are looking at graphs which, loosely speaking, have a tree-like structure, then we can do it in polynomial time, where the speed of the algorithm will depend on how tree-like the graph looks. There's an important open class of counting problems here. We'd like to be able to evaluate these polynomials on square grid graphs, like sort of chessboard graphs of arbitrary sizes. We don't really know how to correctly classify the complexity of that. This is a big open problem. One thing I was interested in some years ago is trying to get as close to this big open problem as possible. So I looked at subgraphs of the square grid where the subgraphs have maximum degree 3 and was able to show that it's still number P hard. So it's still the most restricted class of graphs for which computing these polynomials is known to be number P hard. So that's if you want to compute the entire polynomial. But maybe you're just interested in certain evaluations of the polynomial. Maybe there are certain specific points that you really care about. Maybe you want to work it out at this point because that gives you the number of spanning trees, or that point because it gives you the number of 3 colorings, and that's your problem. That's all you need to know how to do. You don't need to compute the entire polynomial. Unfortunately, there's some bad news there as well. A major result in 1990 was that to determine this polynomial, even for some specific point, is number P hard, except in a few very rare cases enumerated here. And I'll show that in a diagram. This is the diagram we had before of the domain of these polynomials, and the black curves and the black points are where you can do it in polynomial time. All the other points are number P hard. So on the face of it, that's bad news. Some of these black points are still very useful. For example, the one here counts the number of spanning trees of a graph. That can be done in polynomial time. So that's been known since Kirchhoff in the 19th century, and that's fundamental to electrical circuit theory as well. So there is some good news in all this, but most of these evaluations are really difficult. So if we can't do things exactly and we prove hardness results about them, well, okay, that's good, but that doesn't make the problem go away. If the problem is worth solving and we can't solve it exactly, the next thing we ask is, what about approximations? And probabilistic approximations are particularly natural in this context because very many of the problems we're interested in, being problems of counting, are perhaps at heart more naturally viewed as problems of probability. And in many applications, we don't really need to know the exact answer. If I want to know how many timetables are possible, given my current constraints on students and exams, if I want to know how many timetables are possible in order to know how many possibilities I might need to search in the worst case, I don't typically need to know that exactly. It would be very useful to have just a good estimate of it. And the main technique for approximating these counting problems on graphs is fully polynomial randomized approximation schemes, or FPRASs. These are algorithms. So a fully polynomial time randomized approximation scheme for a function f, some counting thing on graphs, is an algorithm that runs in polynomial time. Its inputs are the input for the counting problem that I'm working on, and for us that will usually be a graph, and also some parameter specifying how much error I'm allowed to have in my answer. And the algorithm runs in time bounded by a polynomial, not only in the input size, but in the reciprocal of the error parameter. So loosely speaking, the smaller I want my error to be, the more time I have to be prepared to spend in getting an approximation to within that error. And having run in that time, the algorithm outputs an estimate that is within that error of the correct answer. So here in the middle of these two inequalities is the ratio between my approximate estimate generated by the FPRAS and the exact right answer. And I want that ratio to be within epsilon of 1. If the ratio equaled 1, I'd have the exact right answer, but I'm saying I want to get within a distance epsilon of having a ratio of 1. So epsilon's putting a bound on the relative error that I'm allowed to have. But I must say, it's not an absolute bound. It's not a strict bound. It's a probabilistic bound, in effect. I'm not saying that I must always lie within that error. I'm saying that my probability of getting within that error has to be high. It has to be at least 2/3. Okay. So I want to get within this arbitrarily small relative error of the right answer with a probability of at least 2/3. Now, a couple of remarks about this before I go on. The choice of 2/3 here is somewhat arbitrary. It has to be any fixed fraction bigger, strictly bigger than a half. So I could have put 3/4, or I could have put 0.9, or I could have put 0.51, as long as it's strictly more than a half. Putting it exactly equal to a half won't work. But as long as it's strictly more than a half, it really doesn't matter what fraction I have here, because I can, if I run the algorithm, I can run it again independently of my first run. And I can run it again, and I can run it again, and get a whole lot of answers and sort of average them or whatever. And if I run it sufficiently many times, I can reduce the error probability to as close as I like. And I can increase the probability that the answer I settle on is within my specified relative error. I can increase that probability to as close to 1 as I like by just repeatedly running the randomized approximation scheme. So that's the power of this, and it actually converges very quickly. I don't need, loosely speaking, I don't need very many repeated independent runs of these algorithms to be able to quickly increase my guarantee to as close to 1 as I like. So this is a really powerful tool if it exists. So let me talk about when fully polynomial randomized approximation schemes exist for evaluations of Tutt-Whitney polynomials. This is the sort of picture we had before, with the thick black hyperbole and the 4 black points representing the points where you can compute the answer exactly in polynomial time. There's one more curve where by using Markov chain Monte Carlo methods, you can find a fully polynomial randomized approximation scheme. So that's a really important curve, by the way. So that's a lot better news than its size on this graph might lead you to suspect. That's a really important result. But we do have a sobering negative result. For a large region of the domain, the whole region colored in pale red here, Jerem and Goldberg have proved that there is no fully polynomial randomized approximation scheme. And that's assuming that RP does not equal to NP. Now, I haven't told you about RP. Think of it as a class of polynomials that have a certain type of randomized polynomial time decider. And RP is a class that is thought of as being very close to P. So the conjecture that RP does not equal NP is believed by the community almost as strongly as the conjecture that P does not equal NP. So this is taken as very compelling evidence that unfortunately in this whole region of the plane, we don't have a fully polynomial randomized approximation scheme. All the white territory is open. So that's a major open problem for the field, to find fully polynomial randomized approximation schemes for other points in the domain of these polynomials, or to come up with this kind of evidence that they don't exist. Okay, so that's a quick review of the theory of counting problems on networks. And that really brings me to the end of my talk. I'll just mention, if you want to read further about this, there's a major new work just appeared. Actually, I just got my copy of this the other day. Handbook of the Tutt polynomial and related topics, come out just this year, contains a rich, comprehensive review of current developments and open problems in this field. That brings me to the end of the talk. Thank you very much.
All right. Thank you so much, Graham, for the very interesting the talk. It was like, you know, it actually opened up for me personally. It actually opened up a lot of like areas to think about that I would like, I would like to work on when like when I have a like do some when I have some time to do some research. It's really interesting. I hope it would be the same for all of our participants. So now let's move on to questions and answers. So if you have any questions, please feel free to ask them. Like I told you earlier, do not think of any question as less important. So if you need anything to be clarified, just feel free to ask. That is really important, especially if you are actually thinking of going into graduate studies. The asking questions is really important. That is how you are going to learn. Not just really for graduate studies. Wherever you are going, whether it is industry or academic research, asking questions is really important. So the platform is yours to ask your questions.
I've got a question for you. How many colours do you need to colour the map of Sri Lanka? Answers in the chat. Adjacent provinces sharing a common border get different colours.
Any thoughts?
Maybe I should put up the picture. Just finding the picture. I'll put it up in a minute. There you go. So you can see a colouring there. That's got 4 colours. Can you do better? And can you do it in 2 colours? What are the national colours of Sri Lanka? Is it green and red?
It's like green, red, and yellow.
Okay.
Yeah.
So if I wanted to colour the map of Sri Lanka green, red, and yellow, could I do that? Or if I wanted to colour it with just 2 colours, let's say green and red, could I do that? Is there any reason to think that I couldn't colour the map just where every province, have green provinces and red provinces? Would that work? Oops, sorry. I mean, if I coloured Western Province green, Northwestern red, that's fine. How would I colour this province? I should have practiced this. I've got to go try and say its name now. Sabaragamuwa.
Yeah.
How do you say that, Sachi?
Yeah, that's right. That's Sabaragamuwa. Yeah.
Okay. I think the way you said it sounded different. I'm sorry about that.
Oh, that's
so if I colour Northwestern red and Western green, what would that one be? I mean, it neighbours them both, doesn't it? So that's no good. So needs at least 3 colours. Is there any evidence that 3 colours is not enough? And this is actually quite a hard question. Perhaps I shouldn't be asking this question, because showing for these sort of NP complete problems like graph coloring, coming up with evidence that something can't be done is hard. Sure, if you've got an appropriate certificate, you can verify it easily, but it's not a two-sided situation. You know, you don't have, if the graph is not three-colorable, in general, there's no really succinct, easily verifiable evidence that you can't three-color it in general. So perhaps, asking this question illustrates why, it gives you some insight into why that's hard. I mean, how could you convince somebody that this map can't be colored in three colors? Anyway, let's not focus unduly on the map. If anybody has any other questions at all, happy to take them.
Does the audience have any other questions? It may be anything related to, like, how to get started on a research related to graph theory, counting problems. It can be something like that. If you want to clarify any doubts, this is your opportunity.
So can I ask a question?
Yeah, sure.
It's not directly related to the content card here, but because I've noticed a few junior undergraduates have joined here, can you recommend a starting point for them to get started with getting into graph theory and all that?
Getting into graph theory, yeah, it's a popular area now. There's lots of good books and other resources. Yeah, I mean, most discrete maths courses these days, mostly if you're studying computer science, you'll have to do some discrete maths early in your degree. And most discrete maths courses do a bit of graph theory. And if yours doesn't, nonetheless, if you find a discrete maths textbook, there's probably a decent introduction to graph theory, to some basic graph theory in it. Yeah, I mean, there's so many, it's such a popular, so many good books. When I was younger, there was a book by Robin Wilson, Introduction to Graph Theory, that was very good. It's been around a while. It's possibly a bit dated now. There's a book by Diestel called Graph Theory. That's probably, if you're just starting it as a computer scientist, that's probably pitched too high and maybe a bit more pure mathsy. There are some good books that do graph algorithms pitched at computer scientists. The name Sedgwick comes to mind, or Sedgwick and Flagellate. Perhaps I'll put them in the chat. They have some good books on sort of algorithmic stuff. And I guess as computer scientists, we're most interested in the algorithmic side of graph theory. So they're good places to get started. Yeah. How to find a good research paper and a topic. Yeah, this is a really interesting question. Getting started in research, if you're an undergraduate, can seem a little daunting. But don't be put off. And if you can find research seminars in your university, try going to a few of them. Some universities will run research seminars pitched at undergraduates, or at least will have some events that undergraduates can come to. There are quite a lot of places these days that run seminars online. So because of the enforced running of things online due to the pandemic, that has created a lot of growth in online seminar series, some of which are pitched at undergraduates. Perhaps I might look up some more of these and send them to Sachi later for circulation. That'll probably mean I can give a better collection of options than off the top of my head, but there is quite a lot out there to find. Finding a good research paper. I think it's important to find something that you feel genuinely interested in and think is important. I think that one of the greatest things in research is curiosity. And I think that's, for me at least, and I think for many other active researchers, that's the most compelling motivation. It's the thing that drives human beings to find out new things. Curiosity is a big part of that. And that curiosity can have a practical imperative. It can be because you really want to solve some problem, like how to cure COVID or something like that. Or it can just be curiosity, just human curiosity, wanting to get to the bottom of things, delighting in solving puzzles. I think that's the best motivation, rather than, I guess some people go into research for prestige or for traditional reasons or whatever, or for reasons of expectation or something like that. But and they're not necessarily bad reasons, mind you, but I don't think they're the kind of driving reason that will lead to the most success in the field. I think if you have that factor of curiosity behind you, curiosity mixed with some intelligence and very much hard work and persistence, will take you a long way. So so there are some journals that do publish some things pitched at undergraduates. On the mathematics side, it's worth browsing the in the US, there's the College Mathematics Journal, there's the Mathematics Magazine. A lot of it is perhaps more mathematical than some computer scientists would be interested in, but increasingly they do publish stuff that has computer science connections. So there's a few thoughts on that. Plunging straight into the research literature can be quite forbidding in these theoretical topics. You can find good journals and look up papers, and hopefully they whet your appetite for the field, but you may find as undergraduates that the level is often pitched a bit high, and it's important that you don't let that discourage you. So if you can identify a source of sort of papers that introduce you to research, but in an expository kind of way to make it accessible for undergraduates, that's really good. And those publications of the Mathematical Association of America do that for mathematics students. So on stuff related to graph theory, that would be a source you could go to.
All right. So I think Saad got your answer. If there are no other questions, Dinika, do we have any other questions or anything else that you want to mention as final remarks?
I guess we're done with questions, right, Sachin?
Sorry, what?
I think we're done with questions. Can we get everyone to turn on their cameras if possible to take a photo? If you all don't mind.
Thank you, Saad. Good to see you. Good question.
I guess we could end the session, right, Sachin?
Yeah. All right. So before we end the session, let me once again thank Graham for the very insightful discussion. Thank you so much, Graham, and thank you very much for accepting our invitation. It was really good to have you here. And I would like to extend my gratitude to the Sustainable Education Foundation team, including Dinuka, Visal, and Akshika, and everyone. So thank you very much for all the support. And And to all our participants, I think you got something out of the talk today, something that would drive you into some doing research in on graph theory and counting networks. So thank you very much for your participation today. We will meet with another topic sometime later. And keep in touch. Thank you so much.
Thanks very much, everyone. All the best. Best wishes for the series in future. And thank you very much, Sachi, for your organisation.
Abraham.